Good afternoon. My name is Martin Schiffner. I'm with the Chair of Medical Engineering at Ruhr University Bochum, and in this presentation I would like to introduce frequency-dependent f-numbers that suppress grating lobes and improve the lateral resolution in line-by-line scanning. At the beginning, I would like to introduce the grating lobe problem of linear arrays and explain a solution that is known as dynamic aperture. I will then propose two methods to compute f-numbers, which are important parameters of dynamic apertures, and describe a simple implementation. Subsequently, I will present the results of 3 experiments that validate this implementation. In the end, I will summarize the most important findings. Let us begin with the motivation. Linear arrays, as illustrated on the right, are among the most popular probe types and facilitate the imaging of superficial structures such as peripheral vasculature and small organs. These arrays widen the field of view near the skin surface by a large element pitch, which is of the order of the center wavelength. This element pitch reduces the number of elements and system complexity. This element pitch, however, also violates the sampling theorem, which requires the element pitch to be smaller than the smallest wavelength over 2. As a result, the point spread function has grating lobes and creates artifacts. These artifacts, as shown below, usually arise close to the linear array. One solution to the grating lobe problem is a technique known as dynamic aperture. This aperture increases image uniformity and suppresses grating lobes at the expense of the lateral resolution. The desired aperture varies with the focus RF, which is illustrated on the right. It is centered on the lateral focal coordinate XF and increases linearly in width with a focal length ZF as a function of a user-defined f-number. This f-number should also increase with the frequency. For large wavelengths, a wide aperture improves the lateral resolution. The full aperture can be used if the sampling theorem is met. For small wavelength, a narrow aperture suppresses grating lobes. This frequency dependence, however, has only been validated in plane wave imaging. So the research questions are: how does one select the f-numbers in line-by-line scanning? And is it beneficial to account for the frequency dependence? To answer both questions, the influence of the aperture width on important properties of the monofrequent focused beam were examined. These properties include the depth of field, the lateral full width at half maximum, and the grating lobe amplitudes. As the aperture width increases, the depth of field and the lateral full width at half maximum decrease. The grating lobe amplitudes, in contrast, increase. In the far field, the grating lobes move towards the main lobe and become wider. Based on this analysis, the following procedure to select a transmit f-number is proposed. First, the image depth is partitioned into n focal zones. The main idea is to maintain a constant depth of field in each focal zone. The depth of field, according to Born, approximates 6.1 times wavelength times f-number squared. The f-number, hence, derives from the depth of field and the wavelength. As a consequence, the transmit aperture narrows with the frequency and acts as a low-pass filter. The apodization weights are frequency dependent and reflect the narrowing aperture. This implies that the transmitted pulses are filtered and the cutoff frequency varies with the element index. We now have a closed-form analytical expression for the transmit f-number, and the application of this f-number does not increase the computational cost of the image formation. The receive f-number, in contrast, derives from the angular distance of the first-order grating lobe in the far-field directivity pattern, which is illustrated on the left. The angular half-width of the main lobe only depends on the f-number. The angular distance of the first-order grating lobe additionally depends on the element pitch to wavelength ratio. The main idea is to enforce a minimum angular distance, chi-lower bound, by using this f-number. This distance, owing to the element directivity, controls the grating lobe amplitudes. We now have a closed-form analytical expression for the receive f-number, and this f-number only depends on the element pitch to wavelength ratio. The frequency-dependent receive f-number requires a Fourier domain beamforming algorithm. A line of image voxels and the RF signals for a focused wave emission serve as inputs. In the first step, the algorithm applies the fast Fourier transform to the RF signals to obtain complex-valued phasors in the relevant frequency range. For a selected image voxel, the algorithm computes frequency-dependent apodization weights, which also include the delays, and then multiplies the phasors by these apodization weights to obtain the weighted phasors. A lateral summation then yields the focused signal in the Fourier domain. An inverse FFT then gives us the focused RF signal in the time domain. A specific sample of the envelope serves as voxel value. The last two steps can also be combined into a two-dimensional sum of the weighted phasors. To validate the proposed f-numbers, 3 experiments using a Sonics Touch research system at a sampling rate of 40 MHz and a linear transducer array with 128 elements were conducted. The excitation voltage was a single cycle at 4.5 MHz, and full synthetic aperture scans enabled the synthesis of line-by-line scans. The number of transmit focal lengths was 3, and the depth of field approximated 1.3 centimeters. Dynamic receive focusing was used. The investigated objects were a wire phantom, a tissue phantom, and the common carotid artery of a healthy male volunteer. The investigated f-numbers included in transmit a fixed f-number and the proposed constant depth of field f-number, and in receive a fixed f-number and the proposed constant angular distance of the first-order grating lobe f-number. For the wire phantom, the usage of the full apertures resulted in grating lobe artifacts and a non-uniform image quality. The widths of the wires increased significantly away from the transmit focal length. This increase resulted in a median width of 564 micrometers and a relatively large interquartile range of 220 micrometers. The fixed f-numbers, in comparison, eliminated grating lobe artifacts and resulted in more uniform wire widths. The median width, however, increased to 663 micrometers. The proposed transmit f-number improved both metrics. The proposed receive f-number achieved even higher improvements. The best result, however, is obtained by a combination of both proposed f-numbers. The median wire width is similar to the wire width achieved by the full apertures. All f-numbers hence suppress grating lobes and improve image uniformity. The proposed f-numbers, in comparison to the fixed f-numbers, reduce median lateral widths by up to 8% and reduce the interquartile ranges by up to 18%. For the tissue phantom, the usage of the full apertures again resulted in grating lobe artifacts and a non-uniform image quality. The median width of the wire targets amounted to 493 micrometers and the interquartile range was 177 micrometers. The fixed F numbers eliminated the grating lobe artifacts and improved both image uniformity and contrast. The median width of the wires, however, increased to 743 micrometers. The proposed transmit F number reduced the median wire width. The proposed receive F number reduced the median wire width further. A combination of both proposed F numbers achieved the best results. All F numbers suppress grating lobes, improved the image uniformity, and improved the contrast by up to 8%. The proposed F numbers, in comparison to the fixed F numbers, reduced the median lateral widths by up to 16% and reduced the interquartile ranges by up to 4%. For the common carotid artery, the usage of the full apertures resulted in grating lobe artifacts and low contrast. The fixed F numbers eliminated grating lobe artifacts and improved the contrast. The proposed F numbers improved the contrast further. All F numbers suppress grating lobes and improve the contrast by up to 62%. The proposed F numbers, in comparison to the fixed F numbers, improve the contrast by up to 6%. So in conclusion, closed-form expressions for the F numbers were proposed. In the transmit focusing, the proposed F number maintains a constant depth of field. In the dynamic receive focusing, the proposed F number imposes a minimum angular distance on the first-order grating lobe. A Fourier domain beamforming algorithm was proposed to account for the frequency dependence of the F numbers and the associated apodization weights. The experiments show that the proposed F numbers, in comparison to fixed F numbers, improve the lateral resolution by up to 16%, improve image uniformity by up to 18%, and improve the contrast by up to 6%. The proposed F numbers are easy to implement, and the proposed transmit F number does not increase the computational costs. The answers to the research questions are: the F numbers should derive from the depth of field and the first-order grating lobes, and it is beneficial to account for the frequency dependence. Thank you very much for your attention.